Hey folks, welcome back for another episode of Code Club. Welcome to 2026. As you log in, please feel free to give a shout out over in the comments and let us know where you're calling from, or where you're viewing from. Again, welcome. It's great to have you and be back again for 2026 to do some live streaming of recreating some visualizations that I have found in the scientific literature. Hey folks, welcome back for another episode of Code Club. Welcome to 2026. I'm excited to be back with you. It was about a month of absence of live streams with Christmas and New Year's in the mix and all sorts of other holiday craziness going on. But it's great to be back, and I have a plot that I'm eager to work through with you all today and seeing if we can't make it a little bit better. So as you are joining us, please feel free to chime in with where you are coming from. And it always amazes me the global reach that we see already. I see Leonard from Germany, Noman from Pakistan, Mike from the UK, Hector from Mexico. So really awesome to see that great breadth. And hopefully, if you're like me, you're trying to get 2026 off to a good start. And so I'm glad that you are perhaps trying to prioritize making your data visualizations better, and that you're here to perhaps think about how you're going to do that. And again, we've got more people. Lily from South Korea and Lori, I believe, from Toronto. So again, welcome. As we go along, if you have questions or comments, don't hesitate to put them in the chat. I do my best to look over there from time to time. Hey, LHA from Germany, great to have you, as well as Mark from England. So this plot that I have over here on the left is figure 2 from a paper that was published a week ago, last Wednesday, in the journal Nature. And I put out a newsletter, if you get my newsletter, on Friday, describing how I would go about making this figure in R, but again, at a very high level. And so if you're not getting my newsletter, you're missing out, right? So you can go to rifamonas.org and then click on Join Mailing List and put in your name and your address. I will go ahead and copy and paste these into the chat. And also, if you notice the audio doing funny things or the video doing funny things, let me know. I'll go ahead also and paste in the newsletter. And also, we have the paper from Nature. So I pick papers in journals that are open access and that have data that they make accessible with the figures. And that way, you can get this article regardless of your ability to pay for it, because the authors paid big money to get it, as well as getting the data so that we don't have to worry about kind of making up our own data and playing with that, okay? So one other thing I will point out then is that on Monday, I put up a critique video of this figure. And so I'm not going to go through all the ins and outs of what I liked or didn't like about that figure. But this, we're trying to run it. So I'll go ahead and close that. But you've got the link over in the chat. And and so just kind of very briefly, as I think about this figure too, again, it's a scientific publication. It's a scientific figure. It's in a very highly regarded, high-impact journal, probably the journal with the highest impact factor that publishes primary research. Nature has an impact factor of 50. Again, impact factor is a garbage metric, but qualitatively, at least, I think it does speak to the regard that scientists hold this journal. And so what I'm focusing on is this panel C. And in this paper, what they were looking at was the ability of different cell lines, breast cancer cell lines, to metastasize to different parts of a mouse. And so they basically would take a cell line, inject it into the heart of this poor mouse, wait a few weeks, and then see where tumors would form in the brain, the lung, the liver, the kidney, the bone, and the ovary, okay? And they compared the ability of the wild type strain, if you will, listed over here in the left, this MDA, MB231, HCC 1806, EO 771, those are the cell lines, to auxotrophs of those cell lines. And so auxotrophs are cells that are deficient in these different 6 genes. And so what an auxotrophy means is that a gene is knocked out so that you have to provide the nutrient to enable that cell to grow. And so, again, I don't want to get too far into the science, but I believe that DH, ODH, and GART are involved in nucleic acid biosynthesis, right? So you can imagine if you knock those out, then you've got to pick them up from somewhere else, whereas these other 4 are amino acid biosynthesis, right? And so again, if you knocked out PYCR, I don't know that it's proline. Actually, it is proline. Yep. Then the cells have to get proline from somewhere outside of the cell itself. So from the environment or from the diet or from wherever, right? And so this is what's called a petal plot. And so the further out the bar, the less metastasis by the auxotroph, okay? And they've got this panel B to help describe that. And so one of the things I thought was kind of weird was that it's a shorter bar to indicate more depletion. And we talked about this a couple weeks ago before the break in a critique video that I made of a bar plot that was on a log scale. And that's problematic because a bar plot really has got to have 0 on the y-axis. Otherwise, you can kind of do funny things with the aspect ratio and people's perception and trying to compare areas of different things. And so you can't put 0 on a log scale, right? The log of 0 is undefined. And so what they did here was to do like 0 for no depletion, -1 for 10x depletion, and -2, or basically the center of the circle, as being more than 100-fold depletion. So basically 0, right? And so if they would have set this to -3 or 10 to the -3, like 1,000-fold depletion, then your wedges would start looking pretty different. And so I thought that was weird. The other thing that I thought was weird is that they have these error bars on each of the petals. And so you come over to like this 5th column, BHGDH in the middle for OV for ovary, right? And so they've got the error bar inside, but it doesn't go to the outside, and it should be symmetric. And actually, if you look up here at B, you see the symmetric error bars. And then also over here, this PYCR in the same HCC cell line, we saw in the critique video that this actually extends beyond this, right? So the auxotroph actually metastasized better, not significantly, but better than the wild type. And so it just, I think they're pretty plots. I think they're kind of cool. But when I started scratching the surface on these, I was left wanting, right? And so what I'd like to do in today's episode is maybe quickly show you how we could make a petal plot like this. I'm not going to try to gussy it up and make it look pretty like theirs. And then pretty quickly try to move on to thinking about a different way to visualize the same data that might be easier to interpret and, I don't know, just perhaps what I would think of as perhaps being an alternative way of representing the data. All right. So we have more people here from Germany. And it's great that Fabian says that data visualization is part of his job. And so he can watch the video during work. And so I would hope that if you're a graduate student or postdoc, that you could say the same thing, right? This is part of your professional development. So with that in mind, though, if you have ideas or suggestions for things or data visualizations you'd like me to comment on, by all means, shoot me an email at pat@rifamonas.org or leave it in the comments with a link to that figure, and I would be happy to satisfy those professional development needs, okay? So, like I said, one of the things I like about these Nature papers, not all of them, but many of them, is that we can get the source data that went into making this plot, right? And so that's in source data figure 2. And when I hover over this, it's perhaps impossible to see, but in the bottom left corner, it is an XLSX file. So I'm going to go ahead and copy the link address. And then I'm going to fire up our studio. If I can. There we go. And I already have a file called metastasisplot.r. And all of the code that I'm going to generate, I'm going to be posting to a blog post. And so if you look down below in the description to this, after I finish recording, there will be a link there to where you can go to get the code as well. So I'll go ahead and paste that link in. And so you can see that is an XLSX file. I'll put it in quotes, and I'll call this petal data. Right? And then let's go ahead and do library tidyverse, because I know I'm going to need the tidyverse. We'll go ahead and do petal data. And then we're going to do download file. And of course, I could click on that, download it to the directory, and then move it to wherever I want. But what I would like to do is go ahead and save this to my working directory. And you can see my working directory is metastasis plot off of the desktop. So the URL is petal data. And then I'm going to call this the destination file. I'll call petal data.xlsx. Run that. That downloads it. Now, if I go look at files, I see that I have petal data xlsx stored in there. And I'm going to go ahead and, let's see, there we go. I now have that file. So I'm going to go ahead and open it up in Excel. And we've got, I'm going to not try your name, but got someone from Italy joining. So what about a multivariate visualization? So I think this is a multivariate visualization, right? In a way that we've got, I guess it depends on what do you mean by multivariate visualization, right? So we've got the cell line, that's one variable. We've got the auxotroph, that's another variable. And then we've got the organ, right? Where the metastasis was formed, that's a third. And then we have the level of depletion. So that's 4 variables. So maybe what you mean is like multiple dependent variables, right? And so that's, of course, a different type of question. And I will definitely be looking for those. And again, if you have ideas for those types of visualizations, send them my way. So anyway, here is the Excel file. And I don't know that putting data in an Excel file is necessarily the best way to do things, but it works and it's what nature requires. So I'm not going to argue with them. But what we can see here is that we've got a fairly tidy data frame, right? And so we have the cell line, the gene, the tissue, the mean, the median, the lower and the upper confidence interval. So this is really nicely formatted. And we can see there's 108 rows plus the header. And so that corresponds to all those different variables. So 3 cell lines, 6 auxotrophs, and 6 tissues, and so that's 108, okay? So let's go ahead and read this in, and we'll come back to R, and we'll do read Excel. And that is a package that actually is installed with the tidyverse, but we still need to load it separately. Actually, I think that's true, but let's test it, right? So we'll go ahead and do read Excel petal data.xlsx. Yeah, so you have to do it. So let's go ahead and do library read Excel. And now when we do it, we see that it reads in our file and everything looks pretty good. One thing that we notice is that cell line has a space in it. So to use that variable cell line, we're going to need to put it in quotes or change its name. And so maybe what I'll do is change its name. And so I'll do rename, and we'll do, I always forget the order, if it's the new name equals the old name or the old name equals the new name. I think it's new equals old. So let's try that. So we'll do cell line with an underscore equals cell line. And I didn't get any errors, and it did the change for me, okay? So cool. So now, again, what I'm trying to do is build that, a basic version of the petal plot, okay? And we've got Matthew from Australia. And of course, we have the obligatory call out to janitor of clean names. And there we go. All right. I don't know janitor because I find knowing rename is easy enough for me. But maybe someday I will get around to making a video about janitor once I've learned some of its features. So anyway, so what we want is we're going to be, let's create this as a bar plot. And so something I forgot to mention is that these petal plots are really bar plots, but in radial or polar coordinates, right? And so it's a lot like how a stacked bar plot in a radial or polar coordinates is a pie chart, right? And so by taking like a dodged bar plot, we can then represent that in polar coordinates to get this petal appearance, right? And so let's go ahead then, and we'll do ggplot, AES, and then along the x-axis, we're going to put the tissue. On the y-axis, we're going to put the mean. And then, what? And then the color, or the fill, is going to be the gene, right? And then we can do plus geom bar. Okay. And let's see how this goes. Oh, it's complaining. So it should be geom call, sorry. Very good. Let me hide my face. There we go. So we see that we've got now a stacked bar plot, and it's actually going negative, right? And it's adding up those values. And so I think what we need to do is to modify the mean to subtract that from 2. So we'll do mutate mean equals 2 minus mean, or maybe it should be 2 plus mean, right? So if it's minus 2, then it's going to be 0, right? And so then we can then pipe that into this. And so now we see that. Right. And so it's adding the values also across the cell lines. So what we ultimately want to do is to facet this. So we'll do facet grid. And across the rows, we want the gene. And then across the columns, we want the cell line. And I might have the order of this formula notation switched, but we can change it if it's wrong. And sure enough, I have it switched. So let's go ahead and put cell line tilde gene. And so now what we can see is that we have our bars, right? With our rows being the different cell lines and our genes being the different columns. I'm going to go ahead and write this out to ggsave, and I will call this metastasis plot.png, and I'll do width equals 7.5. So the one of my critiques of the original figure, I don't have panel D in here, but panel D goes off to the right further. And so they didn't use like the full width of the figure. And maybe if I come back to this, right? So you can see here that panel D goes over the full 7.5 inches. There's half-inch margins. And then this panel C, they shortened it. Like, why? Why not just use all the space that they give you, right? So I don't know. That's kind of one of my constant pet peeves here. So let's do width equals 7.5. And then I will do height equals 4. Let's see what that looks like. And I will open that up. And so now we can see that we've got those bar plots going all the way across. And let me kind of put these side by side a little bit. So we have like the ASNS and the first one is E0771, right? So this panel corresponds to this down here, right? And so you can kind of see that, yeah, right? So like these four, whatever they are like the lung, kidney, liver, ovary, whereas this one here is probably bone, and then this one at 1.5 is brain, right? Okay, but to make the petal plot, we want to flip this then into polar coordinates. And so to do that, we can add chord radial. And there we go. That's kind of a mess, right? We can save some room by getting rid of the legend. So let's do show.legend equals false. So that gets us a bit more room, right? And this is our our plot. And there's a lot that we could clean up in here. And maybe I kind of can't help myself to some extent. Let's, for Oh, let's see. Hey, we've got someone from Turkey and BC, Canada, British Columbia. Awesome. Welcome to everybody. It's great to have so many people tuning in. We've got 19 people watching right now. That's awesome. Let's see if we can get that over 20. I tend to get about 15 to 20 people viewing, so if we could get that over 20, that would be awesome. So I don't want to spend a whole lot of time messing with this figure, but maybe I'll spend, let's say like maybe another 15 minutes or 10 or 15 minutes playing with this to maybe make it look a bit more like this original, if that's okay. And so let's then set that aside. And yeah, okay. So let's then, let's start with maybe making those wedges a bit more narrow, right? So like if we look at these wedges, I want to say that there's like 6 wedges here, but there's space for 1, 2, 3, 4, 5, 6, another 6, right? So like each wedge is 1/12 of the whole radius. So let's come in here and then do like width equals 0.5. And so that actually looks pretty good, right? One thing I'm noticing is that there's a hole in the middle and that there's extra space on the outside, and that corresponds to the expand on the y-axis, okay? And so let's go ahead and turn off the expand entirely. So we'll do expand equals false. And so then that got rid of the center, like kind of the donut feature, as well as the border around the outside. But what we need to think about in radial coordinates is that the x position gets mapped to the theta, the angle, and that starts at like 12 o'clock on a clock face, whereas the y value is getting mapped to the radius, right? And so we need a bit of space up here at the top, and we also need to move bone to be at 12 o'clock. Well, that's ultimately going to be brain, but whatever. And so what we could do is to add in here then, I believe, xlim, and this is going to be, let's see, we're going to do, I think 2 times pi times, and we'll do, so we want to add like 1/12 to the beginning and the end, I think. Let's see, it didn't like that. Xlim. Maybe I need to do this separately. So let's go ahead and do scale x continuous, and we'll do limits equals that. So those are on a continuous scale. All right. I think I need to set the expansion units separately, because I think what I want to do is, instead of playing with the limits on a discrete scale, I think what I want to do is play with the expansion on the discrete scale. So let's go ahead and pull that out, and we'll do scale y continuous, and we'll do expand equals c 0, 0, and then we have scale x discrete. So this expand c 0, 0 turns off all the expansion, and here we can then do expand equals c, and I'm going to do 1/12 0. And I think I forgot a plus sign here, so we'll get that going. And looks pretty good. Feel like that's maybe not quite big enough, but I think that's probably about right. Let's go ahead into the help of chord radial. I don't do a lot with chord radial. One of the comments I made in the critique video was that I felt like if you need to put things on a circular coordinate system, see pie charts, phylogenetic trees, you're probably doing it wrong, right? There's probably a better, easier way because that angle is just hard to work with. So with chord radial, there's a start position that we can use. And so let's go ahead and do that. So we'll do start equals, I think it's going to be minus 2 times pi divided by 12. And so this start in 0, as we can see down here, offset starting point from 12 o'clock in radians. So that's why we need the 2 pi. All right. And there we go. And so I feel like that's not quite like, so bone is at 12 o'clock, liver is at 6 o'clock, and I feel like this space to the left of bone is larger than the space to the right of bone. And so maybe it should be like 1/12 and 1/12. And that looks better. Okay, so now we have a value at 12 o'clock and 6 o'clock, and then like 2, 4, 8, and 10 o'clock, right? Which looks pretty nice. Okay. Yeah, so welcome Mohammed from Indonesia. The script that I'm developing will be available at a blog post that I will post a link to down below at the end of this session, okay? So, some cleaning up stuff that we might think about doing. Again, I don't want to spend a whole lot of time talking about this one visual today, is maybe thinking about like the grid lines, right? And so let's go ahead then and into theme, we can do panel.grid minor equals element blank. And so that got rid of those more fine scale grid lines, right? But in the original, they had one at like basically -2 or 0, 1, and 2. So to do that, what we could do would be in scale Y continuous. I can put in here breaks equals C 0, 1, and 2. And that should give us then major grid lines at 0, 1, and 2 on the radius. And so now we see that, right? And we could go ahead and what? Let's go ahead and flip the color. And so we could do panel.background equals element blank. And we could do panel.grid.major equals element line. And let's do like color equals gray and line width equals 0.3. And so that then gives us that appearance, right? And so you'll notice that like there's a grid line for the theta that corresponds to each of those x-axis coordinate values. So let's go ahead and turn off the y-axis text and ticks. That's basically these values out here to the left. And so with that, we can do axis.ticks, or let's do text.y equals element blank. And so that got rid of the text, the numbers over here, but we still have the ticks. I noticed the original didn't have ticks for the x-axis because those might get confusing with the confidence interval. So let's go ahead and turn off all of the ticks. So we'll do axis.ticks equals element blank. And that got rid of that. We could also get rid of the y and x-axis labels. And so again, we could do that within labs, but we can do it here since we're already working within theme. And I will do axis.title equals element blank. And that gets rid of that, which is great. Now what I'm thinking is that it would be nice to get the labels from the right side onto the left side, okay? And so to do that, we can come into facet grid, and I'm forgetting on the argument. So let me do facet grid, and it's going to be something like switch, which I think this might be it. So switch, where are you? So by default, the labels are plotted on the top and right. If X, the top will be displayed on the bottom. If Y, the right will be on the left. Okay. So we're going to want to do switch equals Y. Very good. Now we have those labels on the left side, right? Nice. And one thing that they did was they turned their labels 90 degrees. So let's give that a shot. And to do that, what we'll do is that's the strip. So we'll do strip dot text dot Y, and we're going to want to do left because it's been flipped to the left side. And so then we'll do element text. I'll do angle equals, I think it's 0. It's either 0 or 90. We'll figure out soon enough here. And there we go. It was 90, right? And so now what I want to do is remove the background from those strips. And so again, I can do, or sorry, the angle is 0, not 90. So I'll do strip.background, and I'll do element blank, and that will remove the background from all of my strips. And so that gets rid of that, right? And so one thing that I'm seeing is that the text is kind of running into itself, right? And so what to do with that? So we could shorten the text, we could bring it closer, we could make the text smaller. I think, looking at theirs is right justified on those labels on the strip. So maybe on that, I'll go ahead and do hjust equals 1 to make it right justified. And so that is like bleeding into those labels, which is unfortunate. One thing I kind of liked that they did is that they had their labels perpendicular, basically, to the text, whereas ours is much more like this. And so I forget how to do that, though. So I'm going to open up my browser, and I'm going to do ggplot2 chord radial labels perpendicular, and see if I can get help. I feel like I've been here before, and let's see. Like a lot of these seem like very long answers, and that's not great. But I see now part of ggplot2 3.5 is that we can add guides. So we can add guides, theta equals guides axis theta, angle equals 90 to get to be like that. And if we do 0, it's going to have the look we want. So I'm going to go ahead and copy and paste from Stack Overflow. Hope no one finds that offensive. So we'll go ahead and add that in. And now what we find is that our text is, Our text is perpendicular to the circle. And I think that's cool. Again, the text is still running into the other panels. And so something I will do is like axis text X, I'll do element text. Let's do size equals 8. Make it a little bit smaller. That's a little bit smaller. Maybe we could go down to 7. And so that's smaller, but it's still kind of running into the other stuff. And so maybe what we could do is like shrink the margin between the text and the plot. And so we could do like axis text X, and then let's do, I think we could do margin in here. We'll do margin, and then it is the bottom margin. So we'll do B equals 0. And that brings that in, right? And I think that looks, right? So like I said, I don't want to spend a whole lot of time on this petal plot, but hopefully you get the idea, right, of kind of how this is being done. And there's other things that we can do. I guess like the first thing I would do would be to reorder the cell lines, reorder the auxotrophs, reorder the tissue sites, right? So we could do that with factor. Again, I'm going to hold off on that. One thing that I haven't added that I think I'll go ahead and add are those confidence intervals. So I'll add the confidence intervals, and then I'll kind of put this to the side. So to do that, we're going to do geom error bar. And for this, we need the aesthetic, right? So we need like ymin, and that's going to be, well, I'm forgetting what it's going to be. I think it was CI lower and CI upper, right? So I'll go ahead and copy these up, and then we'll do ymax equals CI upper. And let's go ahead and put these on separate lines, okay? And so now we have that aesthetic ymin, ymax for geom error bar. And so now what we get are our error bars, but they have not been transformed by subtracting the values from 2, like we did for the mean, right? The other thing is that they have the hat on the error bar, which we want to get rid of. So let's see, back up here, we did this mean 2 plus mean. And so maybe what we could do here would be like CI upper equals 2 plus CI upper, and CI lower equals 2 plus CI lower. And that looks good, but we need to get rid of the hat. And so what we can do back up in geom error bar then would be width equals 0. And that gets rid of the hat on the error bar. And so again, my ordering is different from theirs, but like this is down here is this DH, ODH in the EO, right? So this corresponds to this, right? And so again, everything's out of order, but you kind of get the idea of those error bars. And the width is, the line width is too thick. So let's do line width equals 0. Let's try 5. I didn't do much. So let's maybe take that down to say 0.3. And I think that's a little bit cleaner, right? So hopefully you can see how this works. There's a suggestion in the comments for panel spacing. We could try that. So let's try panel.spacing. And there's an X and a Y, but I think panel spacing will do it in both directions. And then we give it, let me see. It takes a unit argument. Okay, spacing equals unit. And then let's do like 3 points. So that made them closer. So let's go up to say 10 points. And that makes them further apart, right? So yeah, you could play with that panel spacing as well, both on the X and the Y, right? So if we wanted to be 10 on the X, then that's gonna make them 10 units apart on the X. And we could also do like on the Y, I need a comma here. And then let's maybe make this 20. And that makes them further apart, right? So again, the only thing left to do for these would be to get the orders right and then to get the fill colors to match. And so I'm going to save that because we'll probably end up doing that in the next iteration of the figure, okay? And so maybe what I'll do is I'm going to go ahead and call this metastasis petal plot, and we'll then have that saved, and all this code will be available for the petal data. And so, yeah, so hopefully this makes sense and you don't mind me kind of shifting gears here a bit to looking at a different way to represent this data. Like I said, I think there's just generally some problems baked into this. And one of the things I noticed was that, Like the, let's find an example here for like this liver EO771 ASNS with liver, ASNS liver. So that would be in here, right? So the let's see, that column is the median, but the mean is 0, right? So that goes out to 2, and then it comes in negative 0.22, but it goes out to 2, right? So it doesn't have like the full mirror of the confidence interval. Now, I would assume that it's going to be plus or minus the same value, but I think we saw other things like where, like this liver value here, where it's going beyond the outer boundaries. And so I think what would be better is to go back to the original data, and that's what we're going to try to do next. So I'm going to put a pin in this for now, if you don't mind, and let's look at the more raw data. So one of the things that I kind of appreciated about this version of the figure is that it's a summary of the data, that they repeated these experiments like between 3 and 7 times for the different auxotrophs, the different cell lines. And so they present that data in their expanded data, I believe 8, right? So that's this extended data 8. And so these jitter plots that you find correspond to what they had in the original, right? And so let's find an example here. So like this MDAMB, that's the first row. And then we can look at the DDOH. So that's this right here, right? And we can then see that basically the black line, the black circles are the wild type and the blue are the auxotrophs, right? And so in this case, like the mean is about almost 2 units different from all of these, right? And so because we're working on a log scale, if you take the difference of 2 log values, that is the same as the log of their ratio through rules of logarithms, right? And so you can kind of see that hopefully. And so I guess another example would be this like EO771. This here corresponds to this down here in the lower left corner. And like one example I was talking about would be like the ovary, right? Where the auxotroph mean is larger than the wild type mean, right? So if you kind of look at this out here, it's not statistically significant, but you can kind of see how they represented that here. And so what I would like to do is something a lot like extended figure 8, but showing the synthesis of the data, showing the mean depletion with those error bars, okay? So again, extended figure data 8 has source data. So we'll go ahead and click on that. And that is here. And I'll go ahead and copy the link address. And I'll go ahead and throw that in the chat if anybody wants to play with that. Oh, we're up to 21 viewers. Awesome. Let's see if we can get up to 25. So stick around, and as more people join, then we'll hopefully see that number go up. Oh, we went down to 18. All right. This is why I don't try to watch that too closely. All right. So let's come back to our studio, and we'll again do download file, and the URL I'll put as its own variable. And so this is raw metastasis data, right? And then we'll take raw metastasis data, and that doesn't need to be in quotes because that is a variable representing the URL. But I will then call it raw metastasis data.xlsx. And so that gets that downloaded, right? And so it's always helpful to open these files to see what they actually look like. And so whereas the figure 2 data is nice and tidy, I noticed that this data is not tidy, right? We have each gene and cell line being represented as a different chunk within the table. And then like there's a column heading for control that is I believe 7, or it's probably actually 14. Let's see. Yeah, so it's 14 columns wide, right? So I think I said 7 before. I think it's between 3 and 14 replicates. And then they have the knockout going off to the right. So their replicates are in separate columns rather than in separate rows. So we want to read this in. This is actually also in the second tab. The whole body BLI corresponds to the whole body bioluminescence, right? That's kind of for each panel, like here. The left side is that whole body, and the second panel within panel A corresponds to what's in this tissue BLI log 10. So we're going to want to save that information because we're going to want to read in that file. And so we'll again do read Excel, and we'll do raw, nope, it's going to be in quotes, raw metastasis data XLSX, and we'll do sheet equals tissue BLI log 10. Okay, so we read that in. Let me take a drink here real quick. And we can see that it very much looks like what we had in the Excel workbook, right? Where we have the cell line in the first column, the gene KO, tissue, so forth, and that there's kind of like a 2-row break between each of the blocks of text. And so what I'd like to do is remove those rows where the cell line value is NA. So we can do that with drop NA, and I could do drop NA, just open close parentheses, but like these values over here are going to be NA values. And so if I do drop NA, then I'll basically lose all my data. So we're going to want to do that on the cell line data, okay? And so let's go ahead and I'll do that rename again, and we'll do cell line. Well, you know what? I'm going to sit tight for now, and I'll do drop NA on cell line. That needs to be in quotes. And so then that, that got rid of the NA values, right? And so we go from this ASNS to ASS1 and so forth. And so then we should have 108 total rows, right? Because we had 6 auxotrophs, 6 tissues, that's 36, and then 3 cell lines, that's 108. So that works, okay? And then the problem is that we have all these extra columns for the control and the knockout. So what I'm going to do now is to, I think I'm going to actually rename the columns back up in Read Excel. So what we'll do is call names, and I'm going to give it a vector of column names. So we'll do cell line, auxotroph, or let's say gene, because that's what we had called it before, tissue, and then we'll do P original. I'll leave that in for now. And then we're going to have 14 controls and 14 KOs. So to do that, I'm going to use the glue package, which is installed with the tidyverse, and it has one function, which is glue. And so then what I'll do is glue, in quotes, CTRL underscore, and then in curly braces, 1:14, curly brace. And then I'm going to do the same thing, but instead of CTRL, we'll do KO. KO. And I think I need to skip a line because I'm reading in the column names. So I think I need to tell it to like skip a line, but I'm not positive. And I think I'm missing a closed parentheses. Yeah, right here. I think. Yeah, okay. Oh, it's unhappy. Let's see. What are you unhappy about? Oh, I forgot to close parentheses right here. Okay. There you go. There we go. Now it reads in nicely, right? And so now I do need to skip that first row because it's reading it in as data. And I can do that by coming in here and do skip equals 1. That then gets rid of that first row. So again, this is what we had before I did the skip equals 1, where the first row of the data frame were the old column names. And so I'm giving it my own column names, but to do that, I need to then tell it to skip that row, right? And so now what I'll do is drop NA on cell line. And so I went ahead and removed that space. And so now we're back to basically where we were, but we've got good labels for all of our columns. To get it to be tidy then, I need to go ahead and do pivot longer. And we will do pivot longer. Let's see. We want to do everything but cell line, gene, tissue, p original. So we'll do calls equals, let's do matches, and we'll do back D. And that should match a digit in the column name, okay? And it's unhappy because it says it can't combine control1 character and control2 double. So I've got control1 as a character. I'm wondering why that is a character. That seems weird. So let's go ahead and do a pull on CTRL1. And I'm actually wondering if my KO1 is also a character. Yes, that's a character. So I wonder if that has something to do with how I did that skip of the first row. These all look like numbers. There's no text in those, okay? And so maybe what I could do is to modify, let's see, let's modify control1 and KO1 to be numerics. So what we can do then would be to do a mutate on CTRL1 as dot numeric on CTRL1, and then we'll do KO1 equals as dot numeric KO1, and then I don't think I need this pull anymore, so I'll comment that out. And so now this pivots nicely without any error messages, and my value column is of type double. And the only kind of funky thing is like this P original is coming in as a character rather than as a double. And I believe that's because it also has less than sign. So let's try that. So let's try P original. And yeah, it's like we've got that less than sign, right? So maybe what I can do, because I have reasons, let's do P original equals str remove on P original, and then we'll remove the less than sign, and then we'll say, let's wrap that in an as dot numeric, and get a closing parenthesis here. And so now I'll comment this out, and I think I'm missing a parenthesis. Nope. Okay. Now when we run that, we see that our P original is a double, and that's good. And that our name and our value is like so. Maybe something we could do would be to give it, I don't know, a better name. So we'll do values to, let's just leave it the way it is. That's fine. Yeah, let's leave it like that. So the name column, though, has useful information in it to tell us whether it's the control or the knockout. And so what we could do would be a mutate on name to remove that underscore. So we'll do str remove, and we'll do name. I have to say, by doing these live streams, long ago someone told me that I should use string remove, because before I would do str replace, where I would replace like basically the underscore _d star. So that's removing a underscore followed by 0 or more digits. I would then do like this, replace it with nothing. And I said, if you use str remove, you don't need this argument. So we run that. And so now what we see is that we have control. And if I look at the bottom, if I do tail, or actually, yeah, well, if I do tail, I then see I also have the KO. But I also still have these NA values in here because not everything had 14 observations, right? And so that was filling those with NA values. So let's do drop NA. And so now what we can see is that we no longer have those NA values, right? So the glue package has more functions than just glue. So there's, so querying SQL databases, okay, cool. I guess all I ever use it for is glue. So thank you for that comment. I appreciate that. Because I'm showing the bias of how I use things. All right, cool. And let's go ahead and remove this commented out code. And so now we have our data in a tidy framework. That took us 15 minutes, all right? All right, so let's think about how we might make something like, what? Oh, that's not what I want to make. Let's pull this up. Something kind of like these jittered plots, right? And so I'm thinking of these as being like faceted. The rows are the different genes and the columns are the different cell lines. And then within those, we have the tissue and the experimental type, right? So we could then go ahead and pipe this to ggplot, AES. X then is going to be the tissue. Y is going to be the value. And the color is going to be the name. All right. And then we're going to add to this, if I can get the right key, facet grid. And I'm already forgetting what I did before, but I think it's going to go gene tilde cell line. So let's see what we get here. It will not surprise you, perhaps, to know that if I can get rid of my face, having keyboard problems. Okay, I forgot to add the geom. All right, so I need to add geom jitter. So we'll go ahead and do geom jitter, add that in. And there we go. And that's very hard to see. Where we have, again, the cell lines across the top, we have the genes across the rows, and then the tissues within each of those panels, okay? And then the data are jittered. So let me go ahead, excuse me, let me go ahead and I'm gonna copy my GG save statement here, and I'm gonna do metastasis dot plot, and let's open that. And so that looks like that. And you can kind of see the jittering. We can make the points a little bit smaller. So we could do like size equals 0.2. And so those get smaller. And we could probably also decrease the jitter. But I want to, so this plot was already made. I don't want to recreate their plot. I want to make something kind of like their figure 2. And so I'm thinking about what are the most important variables, right? Or let's take another step back. What is the actual question, right? What are they asking and what are they trying to answer with these data? So I'm noticing something as I'm talking. I'm noticing that, yeah, okay, we'll come back to what I'm noticing. I think what the paper is trying to say is that different auxotrophies metastasize at different levels with different tissues and cell lines, right? And so I could see what? I could see changing how I'm faceting. I could see changing what I have on the x-axis. And then I could see that, we're going to reduce these jittered points down to like 1 point plus or minus the confidence interval. And so maybe what I should do is to go ahead and do that. Let's go ahead and break it down to a single point plus or minus the confidence interval. And that will perhaps make it easier to see what's going on here. One thing that I'm noticing that I was like fumbling over my words with was that you'll notice like this EO771 has an ASNS here, but then these two panels are blank, right? But right below it is ASNS in all caps. And so they are not naming things consistently. So I think what we want to do is change the gene name to be in all caps, right? So if I look back at the original plot, right, these gene names are in all caps. So let's go ahead and put the gene names in all caps and then reassess where we're at. Again, that is in the gene, right? And that's the gene column. So let's go ahead in here and we'll do gene equals to upper on gene. And so to upper will take, if I do to upper on ABC, that should make it, if I put it in quotes, it should make it all caps ABC, right? So now when I run this and get that, I now go down to the correct number of genes, which is 6 autotrophs. Right. So Laura, thank you, Lori. Human gene names are always all caps. Awesome. So I wonder why they mixed and matched, but whatever. Okay. So again, what we want to do is for each tissue, auxotroph, and cell line, we want to get the mean depletion with the confidence interval. And so this is not a paired experiment. They didn't take the same mice and inject both the wild type and the knockout. Right? They had some mice that they gave the wild type, some mice they gave the knockout. And so because of that, we can't do like a 1-to-1 ratio, right? We can't look at the ratio within a mouse and then look at like the average of the ratios. And so part of this is trying to figure out how they did their analysis. And so I'm going to go ahead and take a step back to think about how they got their p-values, right? Because their p-values should tell us something about the difference between the two states, between the control and the knockout, and it should give us something about the distribution, the confidence interval. So to show you what I mean, let's go ahead and do a filter, and I'll do cell line equals this, and we'll do gene equals ASNS, and tissue equals brains. All right, and I put a single equal instead of 2. All right, there we go. So now what we have is the cell line, the gene, the tissue, and we have the KO and the control. All right, so now what we could do would be to pipe this to like t.test. And we could then do value tilde name data equals period. And so data equals period means take the data coming through the pipeline and insert it for the data argument. And this will then do a t-test explaining the value column by the name column. And so when we run that, what we get is this result, the Welch 2-sample t-test. And we see the p-value is 0.025. It's not corrected for multiple comparisons. And so the alternative hypothesis is that true differences in means between group control and group KO is not equal to 0. And so the mean in group control is 7.87. In the KO, it's 7.17. And so that means that there's, on average, some depletion, right? The KO has a lower level than the control. But one thing I'm noticing is that it's using the control as the reference point rather than the KO, because this confidence interval, which corresponds to the confidence interval that they had used, are positive values rather than negative values, if that makes sense. And so, like, if I come back, let's see, if I open up the petal data and remind myself what I'm looking at here, this is the MD, MB, ASNS brain, right? That their difference is negative 0.76, and then their confidence interval lower is negative 1 to negative 0.43. And so it's not exactly the same as what they have, but it's close-ish, I'll say, right? That's kind of weird. So if we did like the KO minus the 7.8, we get negative 0.7 effectively, which is close again to what they had. There's some arguments that we could perhaps change in t-test. If I do help t-test, then we see that there's, so they did a two-sided test. It wasn't paired. The confidence interval was 0.95. Very equal. The variance being equal is set to false. Maybe if we did var equals true, minus that, we get basically like a very similar value. So I don't know that we're going to get exactly bang on to what. Actually, we got the same exact value, which is a little weird. Let me do false. And I think this is the same value, right? Yeah, it doesn't change. So I don't think I'm going to get the exact values that they had. There's probably slight differences in the corrections that they used or how GraphPad Prism, they made theirs in Prism, how Prism calculates a t-test. So I'm not going to get super excited about that. But again, what we get from this are the p-value, we get the confidence interval, and we get the means. But we want to change the order of the values in name, right? And so to do that, what we're going to do is make a factor. So we'll do name equals factor on name. We'll do levels equals KO and CTRL. And so what we find then is that this flipped the order and we got the right sign on those confidence intervals, okay? And now what I'm thinking about is like, how can we do this for all 108 combinations of cell lines, genes, and tissues, right? So how do we do that? Well, if you've been watching, you know that we can do this with map, right? And so let's go ahead and remove this. Actually, let's not remove it. Let's comment it out because I want to like save that code to remind myself of what I'm doing. And I'm going to want to nest the data. So I'll say data, nest data equals everything but, or maybe we'll do data equals, and we'll do what? Yeah, everything but, well, yeah, I think we can do C. I always do everything but, so let's nest name and value. And so now what we get as a tibble for each cell line, gene, and tissue. Okay. And now what we can do is we can do a mutate on, let's do t-test, and we'll do map, and we'll then give that data, and we'll do t.test, and that will be what I had down below here, right? So that was this. Okay, and then that period is really .x, because the map first argument is .x, okay? And so then I need to make that tilde t-test. Okay, so now when we run this, what we get is a new column for the t-test, and it's a type H test. And something we can do to make it tidy, because this H test object is basically this, right? It's like this type, it's not exactly this type of format. It's stored as a list, not as a data frame. But if I pipe this out to tidy, it's going to complain because tidy comes from a package called broom. Okay. And so now when I do this, what I get is a tibble of 1 row and 10 columns. And I could perhaps do map DFR. And this then is going to put t-test in as a data frame. Okay. But it's got this weird $ notation. So what I'm going to do here then is pipe this out to unnest on t-test. And that then raises the names to their own value within the data frame. Okay. So we can get rid of this. And let's go ahead and clean things up. So we'll do select on cell line, gene, tissue, p original, estimate. That's what we're going to plot, right? That's the difference between these two values. And then we're also going to want p-value. I'm going to say p_value equals p-value, just so I don't have to worry about whether I've got periods or underscores. And then we're going to have conf low equals conf period low, conf high equals conf underscore high, right? And it's upset with me. Oh, because I flipped these. That should be conf underscore high equals conf period high. All right. So we now have our data frame, right? And so one thing that we need to do is we need to correct our p-values for multiple comparisons. And so that's going to be done within each cell line and gene combination. At least that's how they did it, right? And so let's go ahead then and do a mutate, and we'll do p adjusted equals the p adjust on p-value. And we're going to do that by the cell line and the gene. Okay. And so now what we get are our adjusted p-values, and can kind of eyeball them, that they're not identical, but they're pretty close. So let me, before I keep plowing ahead here, let me step back and again just go through what I've done here in the last like 5 minutes. All right. So we had a big data frame, if I show you this, that had the cell line, the gene, the tissue, the name, whether it's the control or the KO, the knockout, and then the value, basically the amount of metastasis. And what we're interested in is the difference in metastasis between the control and the KO. And so these values in value are log 10 scale. That's the way they are given to us. So if we look at the difference between these values, which is what a t-test tests, right? It's the difference in the mean between two sets of values. If that difference is different from 0, then you'll get a small p-value. If it's not different from 0, you get a larger p-value, right? And so what I did then was to run a t-test on each combination of cell line, gene, and tissue. And I did that by nesting my data by taking the name column, whether it's a control or a knockout, and the value into its own column. And it did that by each of the 108 combinations of cell lines, genes, and tissues, right? And then I used map to run the t-test over all 108 combinations, right? And then I tidied it to convert from that htest object to a data frame row, okay? And then I unnested the t-test, I got the columns I was interested in, and then I adjusted the p-values, okay? And maybe just to kind of keep things clean, I'll write over the adjusted value back to the real value. And again, as I go, if you've got questions, feel free to holler. I want to compare the p-values. So let's go ahead then and do ggplot AES. On the x-axis, I'm going to put my p-value. On the y-axis, I'm going to put the p original. And I'll do geom_point. And again, if I get rid of myself, you will notice that for the most part, the p-values agree. And we could add in here a geom AB line. And it's not perfect. Like my p-values are a bit larger than their p-values. And there's different ways of doing corrections for multiple comparisons. The default within R is HOLM, H-O-L-M, and that's essentially what they said they used. If I come back to theirs, I believe down in here, let's see, two-sided, unpaired, Welch's t-test with Holmes SIDAC multiple comparisons correction. I don't know what this SIDAC is. That might be what the difference is. But on the whole, you know, where we're looking for significant p-values down here, they're like bang on, right? They're very similar to each other. And so I think we're using very similar methods, okay? So like I said, I'm not going to worry about that so much. And maybe I'll comment this line out and start thinking again about how we can make this plot, right? And so again, we have on the x-axis the tissue. The y then is going to become the estimate. And the color is not going to be the name. Let's leave off color for right now, and we'll do geom jitter. And so then what we see, let me go ahead and save this to the file, is this, where again we have our points for each of the different tissues. We have our points, and I'm jittering it. I shouldn't be jittering it because there's only one point. So we'll do geom point, and I'll remove the size so we can have a larger size. And so that is what we have, right? And so again, if we're above 0, then the auxotroph did better than the wild type, right? So we have some of those over here. And if it's below 0, then it did worse than the auxotroph, right? And so by doing a dot plot like this, we don't have to worry about taking the log of the y-axis with a bar plot, which is weird, right? And then also by doing it like this, we can, we can compare going across within a gene, right? And we can, yeah. So Fabian says, these map unnest functions always look like some deep, dark magic to me. I hear you. I would say practice with it, right? Practice, practice, practice. And I think you'll get there. So maybe what I will do is try to use the same type of faceting that they used and see how that works, right? So before I do that, why don't I go ahead and let me add the confidence interval, okay? So let's do geom error bar, all right? And then our y min is going to be conf low, y max equals conf high. All right, and so we've got, again, those wide error bars. And so let's go ahead and do width equals 0. Okay. There we go. And so now we have our confidence interval. And that is going to be the 95% confidence interval. And something to note is that like our confidence bars look quite a bit smaller than theirs. And that is because their scale went from 0 to 2 effectively, right? Whereas I'm going from 2 to -4, or 2 to -6 really, right? And so let's go ahead and change the faceting back to what they had. So they did cell line by gene, right? And so that gets pretty gnarly. And yeah, that gets pretty gnarly. Which makes me think something. What does it make me think? It makes me think that maybe I want to also flip the y and x axes because these names are running into each other. I could turn them 90 degrees, but that's hard. And so what I'm thinking is like, what is the comparison I want to make, right? The comparison I want to make is within an auxotroph. I want to be able to compare across body sites and then perhaps across tissues, right? Part of me was thinking like, I would even see putting the tissues together instead of having 3 facets for the rows, to have 1 facet for the rows and have the 3 colors be the 3 different cell lines. And that way then you could have the 3 cell lines right next to each other. So why don't we try that first, okay? So I'm going to then turn off the facet grid and maybe do facet wrap and set the color to be the cell line. Let's see how that looks. So when I say turn off, I'm going to comment it. So we'll do facet wrap, and then we'll do tilde gene, and then the color, I'm going to make cell line. Oh, I did face wrap. Some days I feel like doing that, taking a face wrap, facet wrap. And there we go. And that way then we have, that's interesting. We have 2 rows with the 3 genes, and we have the cell lines being colored. Let's go ahead and dodge those points. So within geom point, we could do like position equals position dodge. Oh, and I need to set a width. So 0.25. So it's dodging the points, but not the error bars. We'll come back to that. So let's do 0.5. That's cool. And then let's go ahead and add this position to geom error bar. Right. I think that works, right? And so again, we have the problem with the tissues, and what might be nice, so let's put it on 1 row. Right. So that's 1 row. This makes it easier to see across the auxotrophs, right? And that's cool. I'm curious what happens if we flip the X and Y axis. So let's try that. So let's do Y tissue, X estimate, and let's do X min, X max. And so here now, this doesn't allow us to compare across the auxotrophs as well. as it does allow us to compare. Yeah. I guess the alternative would be to do and call equals 1. Nope. Gene period, I think. Something like that, which is pretty hideous. I feel like that takes up a lot of room, right? So let me go back to having my tissues on the x-axis. Oh, and then I did like the n row. What happens if we do and call equals 1? Yeah, that's not good. Or is that good? No, that's not good because that wouldn't allow us to compare across our auxotropes, right? Like I want to be able to compare across our cell lines, our tissues, and our auxotropes. So by putting the 3 colors next to each other and dodging them, it's very easy to see between the cell lines. By having a facet of auxotropes, it's easy to compare across the tissues. But from this perspective, I can't compare across the auxotropes, right? So if I do n row equals 1, then we get something like that. And so that is doable, right? And the challenge then is that my tissue labels are all running into each other, and that doesn't make me very happy. I also feel like this plot is probably way too tall, so let's maybe make it 3. Something like that. Okay. Could probably even be 2. Something like that. And so I'm wondering if like this cell line, the legend, could be across the bottom, right? And I could then get rid of the y-axis title. So let's do plus labs, x equals null, y equals difference in metastasis. Something like that. And then we could put the legend around along the bottom. So we can then do theme, legend, position equals bottom. Something like that, although that doesn't really help us with those names. They're still running into each other. And so maybe what we could do would be to use like the 2 character names that they had used, right? And so we could also do here like color equals null. And so color equals null should remove that cell line like that. All right, so hey, John from Barrington, welcome. And all right, so like I said, I'm trying to like make this look a little bit more attractive. I'm noticing as I kind of play around with moving things left and right that the points are kind of falling on top of each other more, and so maybe I could increase the dodge width to maybe like 0.75. And then they kind of get too close to each other, I think. Maybe I'll make it like 0.6 and be happy with that. Okay. I think that's okay. And yeah. All right. So now what I'll do is change the order of things. And so this is the part I didn't do with the petal plot, right? So let's go ahead and change the order of the tissues, and we could perhaps use the 2-character label that they used, right? And so let's come back, and I will do, I'll go ahead and do a different mutate. So the mutate up a few lines on line 63 was doing it by cell line and gene. So I want to keep that separate. So let's go ahead and do gene equals factor on gene. And we will then do levels equals, and I'm going to use the levels they used. And can I, it would have been too easy. So I will, let's see. I'm going to put this on my second screen so that I can kind of do this more quickly. So it's going to be DHODH, GART, ASNS, ASS1, PHGDH, PYCR. And we can pipe that. And let's go ahead and put this on a separate line. Well, it's still going off the right side, but we'll break it up. Okay. And so now we see that we've got the same order that they had, right? And that works, okay? Now let's think about the tissues, and we'll do the same type of thing, right? So we'll come back into this mutate. We'll do tissue equals factor on tissue, and we'll do levels equals, and then we'll do brain, liver, ovary. Actually, I'm going to do the order that they have up here, because so we'll do brain, lung, liver, kidney, bone, and ovary. And again, those are all going to run into each other. And so a thought I had would be to go ahead and to use the 2-character abbreviation. I'm noticing I've got an NA here. So I must be spelling something wrong in my tissues. So brain, lung, liver, kidney, bone, ovary. So what am I missing? So there's brain, liver, kidney. Well, let's see what it looks like at this point in the pipeline. All right, so I've got brain, liver, looks like lung. All right, so I got lung. I didn't misspell that. Let's look and see what it's calling lung back up here. Ooh, lungs. It's the little things, right? All right, lungs. And so now we no longer have that NA value. All right, but we don't want to have those names run into each other. So let's see. If we did like axis.text equals element text angle equals 45, we could move those over a bit, right? And get them looking good. I would, let's see what happens if we hold off on this and use the 2-letter abbreviations, okay? And so we can do this again within factor by doing labels, and we'll do BRLU, LI, and I did KI, BO, and then OV. And so that gives us those 2-letter abbreviations. I don't know. What do you think of that? Let me know. I think that I always have a problem with using jargon where, I don't know, like just that people have to keep track of the jargon, right? And so I think if they're already going to have a panel like panel A, then it's, I think, kind of easy to do the translation. I mean, they did the same thing in like B to C, right? Where they spelled out the organ name and then they used the abbreviation. So I don't think it's ideal, but at the same time, I'm not going to worry about it too much. Now what I'm going to do is go ahead and try to clean this up a bit. So this difference in metastasis is too long. So maybe what I'll do is go ahead and put a \n here. And of course, that kind of uses up some more space off to the left. One thing I'm thinking about, though, is that like this is the log difference, right? Or it's a log difference, which is basically the log of the ratio, right? And so I could instead represent this in scientific notation. So I think I'm going to do that. So let's come back and do that, where we can do scale y continuous. And our breaks are -4, -2, 0, and 2. Our labels, I'm going to do glue, because I've got it loaded, right? And I will do some markdown. So we'll do 10 exponent breaks, and then close out the exponent. And then we need for axis.text.y element markdown. But to use element markdown, I need to include library ggtext. Oh, and I think I forgot something. Oh, I forgot a plus sign here at the end of my scale y continuous. And it's upset. Why are you upset? Breaks not found. Oh, because I put that in there. Okay, let's go ahead and take that. Plop that in. No errors. Good. And then we get rats. Oh. So it's doing the exponent for 10 to the 2 and 10 to the 0, but it's not doing it for the negatives. And so I wonder if, I don't know. It could be a lot of things. I'm just going to make it easy and do sup as like the HTML tag and back out the sup tag. And there we go. Maybe that 10 to the 0 could be 1. I don't know. I'm going to leave that. I'm happy with that, and I think that's good. Maybe we could go to 10 to the -6. Thanks, Lori. I appreciate your permission to do that. But cool. All right. Let's think then. Like I'm wondering if I want to go down to 10 to -6. That will kind of compress things a little bit. Let's try it. So let's do -6, -6, and then do limits. -6.3 to say 2.5. And that gives us a little bit more. Maybe we could make it taller. Let's go up to say like 3. Okay, it's probably too tall. Let's do 2.5. Okay. I think that's cool. All right. Now, so I like the y-axis. I'm thinking about those tick marks and the strips. let's go ahead and remove the strip text. We'll do strip dot background equals element blank. That gets rid of that background. Again, that has a fairly similar styling to what they had. I think that's good. And theirs was, I think, fairly clean in that they didn't have a lot of like tick marks on their plots. Maybe I'll remove those ticks. And maybe I'll first add like theme classic. And work from that. I think that's cool. Some people would want to have a separate y-axis for all of these panels. Again, we're going to start compressing things together, and I think it's fine to keep it apart. One thing I'm thinking about adding though is this like a line for the 10 to the 0, because the 10 to the 0 is really like the confident or the no difference, right? And so I will come back up here before geom point, do geom h line and do y-intercept equals 0. And that gets us a solid black line. I think I'm going to make it a gray line and maybe a bit thinner. Line width equals 0.3. Oh, and it's upset with me. Oh, in geom h line, color equals gray. It needs to be in quotes. I knew that. Someone said that. I think I heard. All right. So that's pretty good. I'm not crazy about those colors. And so why don't we change those a bit? Let's see. I'm also not sure that I want the confidence bar in the legend. So let's go ahead and take that out. So what we could do is within geom error bar, we can do show.legend equals false. And so that removes that. Let's play with the color then. And then we can do scale color manual. And then we'll have breaks equals the vector of names, values, and then labels. And somebody actually in a recent episode reminded me that I could, or told me, I didn't know, that I can give a named vector to scale color manual to keep things matched. So we're going to have the EOS 771 equaling something. We're going to have this equaling something. And then this. And I think I need hyphens in there for that, or I need quotes for that name equaling something, right? And so let's go ahead here and I'm going to try something different. I'm going to go to Color Brewer 2. And so this is a great, I think it's a great site for picking colors that work well together, right? And so I've got 3 classes. They're qualitative. I want things that are colorblind safe. And so maybe we could roll with that, right? With these 3 colors. So I'll export these 3 colors. And for now, I'm going to plop those in. And I don't really care what gets what. So I'll put these in anywhere. And then this one. Clean up my mess a little bit. And let's run that. And so that gets me my colors. And one thing I'm thinking is, like, in the original, it went in the opposite order. And so just for fun, because I don't know, the things I think are fun are not what normal people think are fun. Let's move this order a little bit and do that. See if that is enough to redo it without having to use a factor statement. Yeah, that wasn't enough to do it without a factor statement. So let's go ahead and add a third factor. And we'll do cell type, or cell line, equals factor on cell line. And then we'll do levels. And oh, can I just grab those? Great. And I don't know. Copying and pasting is my friend, but of course it doesn't always. Feels like I'm going faster, even if maybe I'm not going that much faster. So anyway, I'll go ahead and do this real quick. Then this should get things in the order that I'm after. Very good. But I screwed something up because the EO is missing. EO 771. I think I'll. Oh, it's an O, not a 0. EO 771, and then right here I had a 0 instead of an O. And so again, if it can't find the factor, it's going to apply it to an NA, and then scale color manual uses a gray like this for an NA value. Okay. There we go. And so now we have the same order that they had, and that's pretty cool. Let's see. I've got like 10 minutes here, so I'm thinking of like what to do. I think maybe this legend could move up a bit. And let's see how to do that. Let's come in here and we'll do legend dot sort of spacing Y, and we'll do unit equals 0 points. Didn't yell at me. It didn't do anything. Let's do legend.margin. And that didn't do anything either. All right. I have a cheat sheet that is somewhere on my desktop. Oh, now I have to find it. That's the problem. Legend spacing.png. Okay. And so if you want to get a screenshot of this, that would be great. So it's, I think, legend box spacing. Okay. So let's try legend box spacing unit 0. Oh, it needs a unit. So we'll take PT. And so that moved it up. I think. Let's remove that. Yeah, that moved it up by including that. And I think that's pretty good. Let's see. If you have any suggestions on other things that I can try here, one thing that stands out to me as something I haven't done is to indicate significant differences, right? So that's also not something that the original indicated, but I feel like if the confidence interval overlaps with the gray line, that it's not significant. Although I know this one isn't significant. So one thought I had would be to change the shape. If it was like open to be significant, or if it's closed to be not significant, if it's open to be significant, maybe I can do that here real quick. So let's try that. And we could do another mutate. So I'll come in here and then say significant equals if else p-value less than 0.05.
maybe I'll just make it illogical, right? So p-value is 0.05, and then in ggplot, I'll do shape equals significant. Actually, I have a better idea. Let's make that fill. And then in geom_point, we can use my favorite shape, which is shape equals 21. And so then I need to set that with scale fill manual. And we'll do breaks equals false and true, because I don't need the quotes. And then values equals, and I'll do shoot. It's not going to be as easy as I thought. All right. Because I'm going to have to put in like all the combinations, and that's painful. So let's not do that. Let's go back to shape. And then we'll do scale shape manual. And I'll do breaks, see false and true, values equals it's 18 and 1. Oh, I forgot a plus sign. Let's see. Curious what my values are on significant, because everything came back as being open. Of course, I don't have enough space here, so I'm going to do like dot last value. Let's do count dot last value $sign significant. Let's do so it's 54 true, 54 false. That seems almost too good to be true. Oh, unless 18 and 1 are both the same shape. All right, that's a possibility. So let's go back to ggplot2 shapes and pick on one of these. So 1 is an open circle, 19 is a closed circle. I did 18. Let's see. So scale shape. Let's do 1 and 19. Breaks values. For some reason, that is not working the way I thought it would work. So let's see, shape equals significant. Let's do count significant. Comes back as that and that. Let's do poll significant. All right. It's not working, and I'm not sure why. Except, there it is. The oldest bug in the book. I had set shape equals 21, which is writing over what I had up here. All right, so my mistakes are like real, okay? So in case you think I know all this stuff perfectly, I clearly don't. All right, there we go. And so then we have significant, false, true. And I could see Um, let's change that. So we could do, not sure that I totally like the way this looks, but we could do like labels equals not significant and then significant. Get rid of that. So something like that. We could get rid of the significant title. We can do that. Again, I did that in the labs. And so we could do shape equals null. Something like that. And I closed my cheat sheet, but I wonder, legend dot, I'm wondering if there's a way to do 2 rows. By row, whether the legend matrix is filled by columns or by rows. Let's try that. Let's do false. Or true. Okay, that didn't work. I think I might need to tell it the number of rows. Legend. Yeah, I'm not seeing it. Let me go back to my cheat sheet. Oh, now I'm printing it. I don't want to print it. Sorry. Okay. Yeah, my cheat sheet isn't helping. So, and I'm printing off a copy of this thing. So anyway, I don't think that's the end of the world to have it looking like this. What do you think? Like, what I'm trying to do is get this not significant to be under that. And maybe what I can do is I could Google it. So ggplot2, put one legend below the other on bottom of plot. Let's see. Just kind of quickly scan through here to see if I see anything. So this is kind of what I want, like legend position equals bottom, but it's doing legend box horizontal. Maybe I want legend box vertical. Let's try that. All right. Hey, there we go. Of course, now we need to mess with our spacing. Legend spacing y unit 0 pt. That brings them together. I think I'm going to go like -10. Maybe -15. That's too far. All right. Let's do -10. And we could do like legend.background equals element blank, because they're kind of writing over top of each other. I think if I do like -15 now, it'll make them closer and they don't write over. What do you think of that? I like that. And so, yeah. And so again, what we're comparing is the petal plots on the bottom to the actual difference in metastasis, level of depletion. In some cases, although it's not significant, an increase in metastasis. I feel like this is a more honest depiction of the data. I feel like by putting the cell lines as different colors in the same chart, in the same facet, that it's easier to compare those cell lines, right? Like I can see that this like purple and orangish track each other fairly well for like DH, ODH. Whereas the green, the EO771, is quite a bit different, right? And so you can kind of make those types of comparisons. Like I said, let me know what you think. Again, this is one attempt at doing it where I spent not even an hour and a half on this particular visualization. I think, like I said, it is more presentable, more attractive, more interpretable than the original. If I were to spend a little bit more time with it, I would make the lines on the axes and the ticks a little bit thinner. I'm starting to feel like ggplot lines are a little too thick. Also, the spacing between the plotting symbol and the text in the legend is probably too large. I'd probably shrink that down. And I will probably do that before I post the code. So if you want to kind of go back through the blow by blow of seeing the code, down below in the description for this episode, you will see a link to a blog post where you can get all of my R code. LHA says the petal plot kind of puts this focus on the not significant parts. Exactly. I think that's a very good way. That's a much better way of putting it than how I've been putting it. Because we're looking at depletion, where it's kind of like the drop in something. Whereas what sticks out to you is the expansion, right? Expansion of the petal. Whereas like you could look in this row here, which is the GART, and be like, was there actually even any data there? Did anything happen? And so I like that way of putting it. Thank you. That the petal plot puts the emphasis on the non-significant characteristics. So thank you for that. I agree. Let me know down below in the comments to this episode what you think, what you would do differently. And yeah, so again, if you haven't subscribed to the newsletter, please be sure you do that. Up at the top of the chat thread, you'll see a link to that. And if you're not subscribed to this channel, come on, man, get it together and subscribe to the channel. Give me a thumbs up. And please tell your friends what we're doing here on Code Club. And I will see you next time for another episode.